thiosulfate should be polar, right? Because sulfur is not the same as oxygen, right? So if we're looking at, that's thiosulfate, right? If we're looking at it, the oxygens are going to be pulling electron density away, but the sulfur isn't. So we're going to have basically a kind of positive here and negative on that side. Okay, Melissa, does that make sense? Cool. Okay. So, erasing this because it's messy and I don't like it. Let us talk about how molecules interact with each other. Hold on, let me click this so it stops pinging me. Okay, cool. So, we're going to see that this chapter is on intermolecular forces. This will be chapter 6, Shelby. So we're going back now. So we've just finished chapter 7. We are starting now chapter 6. We had switched the two just because your lab was on chapter 7 stuff, and I didn't want you guys to be like completely lost with that. So, okay, cool. So let's see what Zoe's gonna say. Yeah, I know, but I do my best. So at least you won't be lost because of lecture material. So, okay, so actually, with doing all these Lewis structures and stuff, we actually talked about intramolecular forces. Those are forces within molecules. We were able to see if bonds were polar or if they were ionic. But now we're going to look at forces between molecules. So we're going to see how molecules interact with other molecules. Interestingly enough, when they're gases, we assume that there are no interactions between molecules. However, when things are liquid, solid, or they're in solution, they are going to be interacting either with each other or other molecules. So let's go ahead and take a look at one. Let's go ahead and do the Lewis structure for this molecule, sulfur dichloride. I'll do it for you. Alrighty, there it is. Sorry, these are kind of ugly. Okay, cool. We're going to see, we remember that this molecule is polar, right? We talked about that. We saw that the sulfur-chlorine bond is polar because chlorine is more electronegative than sulfur was. And we all know that the molecule overall is polar because those chlorines are pulling electron density away, but those lone pairs are just kind of sitting there. They're not doing anything. And so as a result, we're going to have a slightly negative side of the molecule near where those chlorines are, and we are going to have a slightly positive side of that molecule. Like we can kind of say, we cut this molecule in half. Yeah, what's up? No, but it does help to show the polarity here. So that's why I'm going to be doing it that way. Since this is a bent molecule, I will draw it as bent. Yeah, no worries. Well, again, since your stuff is going to be, multiple choice, I would not do a question that's like, these ones are bent, these ones are not, which one's correct, So don't worry about that. Oh my. Okay, that was exciting. Who was that? Was that Zoe? More road rage? No? Ah, it's Billy. Okay, we're getting rid of Billy too. Okay. Okay, cool. So, this molecule has it was loud, yeah. I know. It was startling. We have a positive side and a negative side of this molecule. So, if we were to take another sulfur dichloride molecule, let's see how these would interact together. Do you think if we take another sulfur dichloride, it's going to kind of approach this one? Do you think it's going to approach like this? Or like this? Yeah, exactly. The reason is, remember, this side of the molecule is negative. That's not an 8. This side of the molecule is positive. So, I don't know why I drew that negative one so close to it. That's no good. We will exit out. We do not want to put negative next to other negative. So we will in fact have the positive that's attracted to that. So we're going to see here that these two guys can kind of interact. That is an intermolecular force called a dipole-dipole interaction. So a slightly positive end of one molecule is interacting with a slightly negative end of another molecule. And that's what a dipole-dipole force is, dipole-dipole interaction. Okay, it doesn't have to be the same molecule. We could have we could have them interacting with other molecules. Okay, there we go. We remember that this side, remember, was slightly negative, this side slightly positive. And we remember that oxygen being more electronegative than hydrogen means these hydrogens are going to be positively charged. And so we're going to have a nice happy interaction. I don't know why I drew them so close again, I'm sorry, but this happy red interaction between those hydrogens and the chlorine. Okay, slightly positive attracted to slightly negative. Let's see what Zoe's going to say here. Oh no. Try our favorite method of disconnect, reconnect. And if it's still not working, I'll do it myself. Okay, is it better, Zoe? I will talk for 3 seconds and let's see if it keeps cutting out on you. Better? Maybe? I'll assume so. Okay, cool. So, we can see that polar molecules can interact with other polar molecules. Okay, and that's again called a dipole-dipole. So remember, two poles, kind of ends. So we have a positive end and a negative end. And those are going to be attracted to other positives and other negatives that are kind of floating around there. Okay, does that kind of make sense? Okay. We have a special kind of dipole-dipole interaction. Let's see, let's do water. Between oxygen and hydrogen, which one's more electronegative again? which one's going to be hogging the electrons? Oxygen, right. And so we can have happy interactions between the oxygen and the hydrogen. Right? So the oxygen from one molecule will interact with the hydrogens from another molecule. And just so you know, if we were to draw these as kind of like spheres, oxygen is a lot bigger than hydrogen is. Right? And so, actually, let me fix that a little bit. Let's make them, yeah, that's a good size. So this is really kind of what a water molecule looks like, right? And so we're going to see that another oxygen can actually get pretty close to those hydrogens. Because the hydrogens are so small, since hydrogen is one of the smallest atoms, right? It's just a proton and an electron, very, very small. We're going to see that that oxygen can get up really close to those hydrogens. And the closer that you can make these dipole-dipole interactions, let me write that, closer dipole-dipole is stronger. Okay, the closer your positive and negative are to each other, the happier they are, right? They're going to want to be close together. So because hydrogen is so small, the oxygen from another molecule can get pretty close to them. And we're going to see this is going to be a special case of dipole-dipole interaction called hydrogen bonding. And that is going to be an H attached to fluorine, oxygen, or nitrogen. Okay, and that'll be interacting with some polar molecule. Okay, so there are three particularly electronegative elements. Fluorine, of course, is the most electronegative. And then we have oxygen and nitrogen, which are also fairly electronegative. So the hydrogen that will be attached to one of those three elements is kind of be extra positive. And since it's so small, other delta negative thingies can come up really close to it. And that's going to form some really strong intermolecular forces called hydrogen bonds. Okay? So, these are going to be strong. Okay, by contrast, our regular dipole-dipole interactions, those are going to kind of be medium strength. All right, so those partial positives and partial negatives attracted to each other. Typically, those are bigger molecules, and they're going to be attracted to each other a little bit less. Shh, quiet, mister. Sorry, someone apparently came to the door or something, and so Mr. Barkey here is huffing and puffing. So I don't know if you guys can hear that, but hush, hush, hush. Relax, mister. Okay. Okay, give me a second. It's okay. It's okay. It's just a stranger delivering something. Hush. You're okay. Okay. So, cool. We have two types of interactions right now. Dipole-dipole interactions and hydrogen bonds. Okay, dipole-dipole interactions are delta positives and delta negatives interacting together. And hydrogen bonds, it's the same thing, except the hydrogen is attached to a particularly electronegative atom. And because it's so small, it's able to get really close to other negative atoms. And so it's going to be nice and strong. Okay, so our dipole-dipoles are kind of medium strength. hydrogen bonds, super strong. Okay, you can have dipole-dipole interactions between any two polar molecules. They could be the same molecule, like two sulfur dichloride molecules, or it could be two different ones, like sulfur dichloride and water. We can also have hydrogen bonding, which is hydrogen specifically attached to fluorine, oxygen, or nitrogen. And that's going to be interacting with any polar molecule. So again, it could be another molecule with hydrogens attached to fluorine, oxygen, nitrogen, or it could be just some other polar molecule. Okay? So far, so good? Okie doke. Alrighty. We're going to see we have one more type of interaction here. Because what about nonpolar things? Question mark. Can they interact with stuff? And they most certainly can. We're going to see that we have one more force that is a little bit less intuitive for us. I'm very excited about this question. So let's just say I have some molecule here. Okay, I've got two of them actually. Molecules, random molecules. Maybe they're fairly big, who knows? It doesn't matter. But we know that in atoms and molecules, we kind of just have electrons floating around, right? They're kind of circling the nucleus in various patterns. Maybe at some point they're closer and farther. They're just kind of like swimming around in there, right? Electrons are just kind of going crazy, doing their own thing, moving at the speed of light, just... Occasionally, in a molecule, at one point in time, maybe a lot of electrons are going to be located on one side of the molecule, just by chance, because all these electrons are just crisscrossing all over the place. By chance, a lot of them may end up on one side of the molecule. And since electrons are negatively charged, that makes this just a little bit negative, this side of the molecule. Okay, just because a lot of electrons happen to be on that side. Okay, so electrons randomly grouped. Okay, they just happen to kind of, yeah. So delta means partial, so like partially partial. So evenless. So double delta, yeah. Okay, and as a result, this side of the molecule is going to be just a little bit positive. Okay, just because there are just not as many electrons on that side of the molecule. Alright, and now here's where things get weird. So, now the electrons in our second molecule get kind of curious. They're like, hey, what's going on in that neighboring atom? Or a neighboring molecule. And they'll now swarm to that side just because there's a slightly positive charge on one side of the nearby molecule. These electrons get curious, right? They're curious. What's going on? What's that? So they're kind of looking now over at that other molecule, see what it's doing. They see it's a little bit positive, so they're going to kind of go over there and look at that molecule. As a result, this now becomes very slightly negative and very slightly positive. And for just a brief instant of time, we have an interaction between these two molecules. Okay, so this lasts for a very short time. So hydrogen bonds, very strong, they last a long time. this lasts fraction of a second. So this is just kind of an instantaneous dipole that induces, that means creates, a dipole in a nearby molecule. Okay, so again, electrons just happen to be on one side of the molecule, just randomly. That creates this very, very slight dipole, which then can have an effect on another molecule by creating a dipole in the second molecule in order to interact with the first molecule. And we get this very short-lived, very weak interaction between them. Okay, this is called the London Dispersion Force. Yeah, I know, because this one is kind of the hardest one to really get, because it's just random and it causes another molecule to do the same thing. And of course, if you had a third molecule, it could then also get curious and do the same thing. Okay, this is also called Vander Waals forces. Okay, they're the same name. Okay? I know this is a bit strange, but this can work. Okay, and this, anything with electrons can do this. Okay, so any molecule or atom that has electrons, aka everything, can undergo this force. Okay, so anything with electrons can do this. However, more electrons equals stronger forces. All right, the more electrons you have, the more that can swarm to one side. That makes your dipole a little bit bigger, right? You're going to have more negative on one side, more positive on the other side, and that'll going to be a little bit stronger. However, these are much, 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 much weaker than permanent dipoles. So that would be your dipole-dipole interactions or your hydrogen bonds. Okay, so London dispersion forces, very, very, very weak. Okay, because they only last just, a fraction of a second, and they're just not very strong because it's a slight dipole. Okay, so permanent dipoles, like you have in the SCl2, that's going to be a much stronger force. And even stronger than that would be a hydrogen bond. Okay? I know this is the weirdest one to explain. However, everything except H plus can do this, because H plus does not have any electrons. But, I mean, you don't really see H plus by itself anyway, so let's not even think about that. Cool. So anything can do this. Okay? Polar things can do dipole-dipole. Polar things with a hydrogen on an electronegative atom can do hydrogen bonding. But everything can do London dispersion. Okay, London dispersion weakest, dipole-dipole medium, hydrogen bonding strong. Okay? Let's see what Shelby's got to say. Yeah, of course. Boom, here we go. Okay, so I want you to give me all the intermolecular forces. We've talked about 3 of them. Okay, we have hydrogen bonding, London dispersion, and dipole-dipole. Those are our 3 IMFs, intermolecular forces. I'm going to give you a couple of molecules, and I want you to tell me everything these molecules can do. Okay? So, this one, and this one, and this one, and that one, and that one. Okay, so I'll just write them here on the side so we all have them. We've got London forces. We have dipole-dipole. And then we've got hydrogen bonding. Okay, so these are the 3 options that we have. Okay, so for these 5 molecules, I want you to tell me everything these guys can do. Okay, so just one last recap. Anything does London. Dipole-dipole is for polar molecules. Yes, it is absolutely important for you to draw the Lewis structure, because just looking at these, you probably cannot tell right away if they're polar or nonpolar, right? Because polar things are going to do dipole-dipole. So in order to figure that out, you have to know if the molecule is polar. And so you'd have to do the Lewis structures in order to come up with that determination. Okay? And just for ease of how we're going to mark these, I'll just call these 1, 2, and 3. And, like, for example, once we have the answer for ammonia, the first one, we can say which numbers it can do. Okay? Just to make it easier for how we're going to do this. Alrighty, so is ammonia going to be polar or nonpolar? That's kind of the first thing we have to determine. It's polar, right? It's trigonal pyramidal. That tells us already it's going to be polar. So that's a good thing. So we know that since it's polar, which one of these can it do? Just from knowing that it's polar. Yeah, it can do number 2, for sure. We can definitely do number 2. All right, can we do London forces with this? No? Why not? We certainly can. Everything does London forces. Everything. So, you know what, let's just write that for all of these, because everything can do London forces. Okay, so that was, I mean, it's not quite a trick question, but it's one that might give you pause. So anything can do London forces, okay? However, the London forces are not going to be very, very important here for ammonia. Okay, and then, yes, who said it? Elsa did say that we can also do hydrogen bonding, and that's correct because, remember, there are 3 elements that are required for hydrogen bonding, right? We can have fluorine, we can have oxygen, we can have nitrogen. Right? And so since nitrogen is one of those 3, that'll give us our hydrogen bonding. Right? Does that make sense? That is correct, Marissa. Not if anything else. It has to be one of those three. See, it's nice when we have kind of like rigid rules. So it has to be one of those three and nothing else. We have a visitor. We have two visitors. Anyone remember which one this is? The tongue, yes. That's little Aussie, yeah. Yeah, he has no teeth, so his tongue hangs out. He has the worst farts of any dog. And his are always silent, go figure. So, you just never know, and then just all of a sudden... So, cool. Okay, CH4. It can do London. Can it do dipole-dipole? Yes. I disagree. If we draw the Lewis structure, I'm just going to bring it back here. This is the Lewis structure you get for methane. All of these are all the same, all hydrogens around, so this is a nonpolar molecule. And so as a result, it cannot do dipole-dipole interactions. And of course, since it can't do dipole, it can certainly not do hydrogen bonding either. Okay, so just number 1 for that. Okay, how about nitrogen? Just 1, absolutely. So remember, nitrogen, also nonpolar, because it's just bound to itself. It's not stealing electrons from itself. It's not a polar bond, so it's not a polar molecule. All right, how about hydronium? All 3, I agree. So hydronium will be polar. You'll see that you have a lone pair on the oxygen. And so that means that there's a difference. And so it's a polar molecule, so it can do dipole-dipole. And then we also see that we have oxygen bound to a hydrogen, and that's going to give us our criteria for hydrogen bonding. Yes, you have to have a polar molecule in order to have hydrogen bonding. So if you have hydrogen bonding, and you can just tell that right from the start, it's going to have all of them. So there are definitely some like shortcuts here. You know already right away everything does London. That's one thing you have down. Everything does London. If it can do hydrogen bonding, it can certainly do dipole as well. Okay, and how about our PBr3? One and 2, I agree. Okay, obviously cannot do hydrogen bonding because there's no hydrogen there. So that should hopefully give that away. And if you did the Lewis structure, you'd see it would be trigonal pyramidal, which will always be a polar molecule, right? So you'll get, this will be your Lewis structure. And remember, bromine, more electronegative than phosphorus, will be pulling electron density away. You'll have a polar side over here, and so you'll have a polar molecule. No hydrogen, so no hydrogen bonding. Okay, so just to kind of summarize this stuff, London is everything. Polar stuff, and that's going to be O, F, or N with H. Yeah, Only polar things can do dipole. Okay, everything does London, and hydrogen bonding is our kind of most specific, has to be oxygen, fluorine, and nitrogen attached to the hydrogen. Yep. Yes, that is correct, Elsa. Anytime it's trigonal pyramidal, it will always be polar. Same thing with bent. Trigonal pyramidal has to have a lone pair. Yeah, so I know. Yeah. Trigonal planar may be polar, maybe not. That one we don't know, but trigonal pyramidal for sure will always be polar. Is sulfite trigonal pyramidal? Let me draw it. If it's trigonal planar, you don't know. So let's see. So sulfur is 6, oxygen is 624 plus 226. Okay, 2, 4, 6, 20. 2, 3, 4, 5, 6. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So yeah, it'll have a lone pair. Yeah, it'll be polar. Had to do the structure there to find that out. Okay, cool. Any questions on this stuff? Good. Yeah, hopefully this, again, is not too complicated of stuff. Yeah, exactly. Probably when you think about it some and, digest it a little bit, that'll be that. So, this is half of chapter 6, so we're in good shape, I think. So, yes. So we are going to have our exam next Wednesday, 1 week from today. It will be on Lewis structures, the gas stuff, and these intermolecular forces. Okay, there is still a portion of chapter 6 that we will cover on Monday, but again, it's not going to be of the, supreme difficulty. Okay, so it's going to be of, similar difficulty to what we're doing today. It'll be about the same number of questions, the same idea as last time. Hydrogen bondings have to be polar, and they have to have hydrogen on a oxygen, fluorine, or nitrogen. So I'll write that. And bondings. Yeah. So actually, sample, it is up here. If you wanted to see, scroll up somewhere. I can pin this for you guys. Oops. Don't need to edit it. I meant to pin it. No. Okay, fine. Okay, so that should show up at like the top, just in case you forget. But it will be 5B, 6, and 7. Okay, so that was Lewis structures, gases, and these intermolecular forces. That also includes polarity, right? Polarity and shape, along with intermolecular forces, gas laws. Okay? Yeah, if you want, I can make that due Tuesday so you guys can see the answers. Would that be easier for you? Would you like that? Oh, sorry. I could make it due Tuesday night instead. And then as a result, I could post the answers on Wednesday morning so you could see it before the test. Would that be better? Kind of like what we did last time? Okay, I'll do that then. I will go on Canvas and I will adjust the due date. It will be due Tuesday then. Okay? And remember that last question. Yeah, Tuesday night, midnight. The last question on homework 7. Remember, don't worry about the minutes, okay? So I will change this. It is now due May 5th. Okay, Cinco de Mayo, while you're drunk on tequila, go ahead and finish your homework. And yeah, oh goodness, this is homework 5. What did I just do? Whoops. What did I just do with homework 5? Who knows? Okay, homework 7 is what we're doing. Okay, and then how many minutes for the last problem? Okay, I'll put that in the homework description so you can all see that. Okay? Sounds good. Yes. Okay, so Elsa, as you'll see on the last question on homework 7, it asks about some minutes. I don't want you to worry about that. It'll just be easier if you just calculate the mass of oxygen. That's all you have to do. Okay, cool. Any last questions? Okay, I will upload these to YouTube as always. And I'll upload the lecture notes right now to Discord, so you'll have them. And there we go. So have fun, stay safe, and